Welcome to The Explainer. Today we're not just going to be writing code. We're going to be architects. We're drawing the blueprint for truly great software. And we'll do it by digging into low-level design and the core ideas of object-oriented programming, all through the super practical lens of a Go developer.
All right, so here's our game plan. We're going to start with the absolute fundamentals of good design, then we'll build up our understanding of objects and what makes them tick. After that, we'll see how they all connect, and we'll wrap up by tackling a classic programming puzzle, one that tells you a lot about a language's philosophy.
Okay, first things first. Why do we even need a plan? I mean, you wouldn't just start stacking bricks randomly and hope a house appears, right? Well, the exact same thing goes for building software. So have you ever wondered what separates an application that people are still using years later from one that just becomes this tangled, unfixable mess? It is absolutely not about having the most features. It's about having a solid, rock-solid structure underneath it all. And that's exactly where low-level design, or LLD, comes into play. Think of it as the super detailed architectural blueprint. It doesn't just say, hey, put the login screen here. No, it specifies the exact data structures, how all the components will talk to each other, and the algorithms that make the whole thing come alive. So why bother with all this planning? Well, because a good LLD is your team's North Star. It makes sure everyone is building the same thing the same way. It leads to code that's not just better, but way easier to fix and maintain down the road. And critically, it means your application can actually grow without falling apart. Fundamentally, there are two ways we tell a computer what to do. There's imperative programming, which is like giving it a detailed step-by-step recipe. You're telling it how to do everything. And then there's declarative, which is more like ordering from a menu. You just say what you want. Object-oriented programming, which is our focus, is a really powerful style that lives in that imperative, how-to world. So let's jump into our main architectural style for today, object-oriented programming, or OOP. This is a way of thinking that has, no joke, shaped software development for decades. So, at its very core, what OOP is all about is modeling the real world right inside our software. We create these digital objects, which are basically self-contained little bundles. They hold both their properties, what they are, and their behaviors, what they can do. This is honestly the perfect way to picture it. A class is the blueprint. It defines what all cars have in common. 4 wheels, an engine, you get it. But an object? Well, that's the real thing built from the blueprint. It's your specific car with its own unique color and mileage. Now, any great way of building things has a set of core principles. For OOP, there are 4 pillars that give it all its strength and structure. And really, understanding these is the key to designing great software. Our first pillar is encapsulation. It's a fancy word, but it's all about creating these little protective bubbles around our code. We bundle the data and the functions that can change it together, and then we hide all the internal details from the outside world. And in Go, this is just so simple and elegant. Capitalize an identifier and it's public. Keep it lowercase and it's private to the package. Done. It really is like a pill. You don't need to know the complex chemical formula inside, right? You just use its public interface. You swallow it to get the benefit. This is the power of encapsulation. It lets you completely rewrite the internals of your object without breaking any of the code that uses it. Okay, next up is abstraction. Now, if encapsulation is about hiding the data, abstraction is all about hiding the complexity. It's really the art of showing only what's absolutely necessary. And the car analogy is just perfect for this. You don't need to be a mechanic to drive. The steering wheel, the pedals, the gear shift, that's a simple, clean interface that abstracts away the incredible complexity of the engine. And that is exactly what we want to provide with our code. Our third pillar is inheritance. This is a mechanism that lets a new class build on an existing one, inheriting all its features. It creates this is-a kind of relationship. Now, for those of us in the Go world, this is a really important concept to get, but it's one we need to be very, very careful with. We'll see why in a bit. The idea itself is super simple and powerful. A car is a vehicle. So instead of recoding things that all vehicles have, like speed, the car class can just get it for free from its parent. This is great for reusing code and building these logical family trees of objects. And our final pillar is polymorphism. This literally means many forms. This is the principle that gives our code incredible flexibility.
And honestly, it's an area where Go's philosophy really shines, usually through its beautifully simple interfaces.
Think about the word draw. Its meaning totally changes with context, right? In Go, we can do the same thing. We can create a shape interface that just says anything that is a shape must have a draw method. Then, a circle can draw a circle, a square can draw a square, and our main program can just tell any shape to draw itself without caring what kind it is. Okay, so we've got our objects and we've got the 4 principles they're built on. But great software isn't about a bunch of objects sitting in a room by themselves. It's about how they connect and work together. So this table breaks down the 3 main ways objects can relate. You've got loose connections, like association. Think of it as a friendship. You've got aggregation, like a team and its players. The players can still exist if the team breaks up. But the one we really, really care about is composition. This is a strong has-a relationship, like a house and its rooms. If you tear down the house, the rooms go with it. This idea is absolutely fundamental to writing good, modern Go. So we've covered the principles and how objects relate. But the way these ideas are put into practice can sometimes lead to, well, some really tricky problems. Let's look at a classic puzzle that reveals everything about a language's deep-down design philosophy. I'm talking about the infamous diamond problem. This whole mess comes from a feature in some languages called multiple inheritance. So picture this. At the top, you have class A. Below it, you have class B and class C, and they both inherit from A. Then, at the very bottom, you have class D, which tries to inherit from both B and C. See how it forms a diamond shape? Now, here's the question. If class B and class C both modify the same method they got from A, which version does class D get? B's or C's? It's a huge, dangerous ambiguity. And pretty much every language has a different way of dealing with this. Java just says, nope, you can't do that with classes, and avoids it. Python has a very specific set of rules to figure out which one to pick. And C++ uses a special keyword called virtual to make it all work out. They're all solutions, but they add their own complexity. And this, right here, brings us to the key takeaway. Go's solution is maybe the most elegant of all. It just avoids the problem completely. See, Go doesn't have that kind of inheritance. Instead, the entire philosophy of the language encourages composition, building complex objects by putting simpler ones together. By choosing that strong has-a relationship over complex is-a hierarchies, Go's design just neatly sidesteps the whole fragile mess that creates the diamond problem in the first place. And it leaves us with a really powerful question to think about, doesn't it? Is avoiding complexity the ultimate design principle? It's a philosophy that's baked right into the DNA of the Go language, and it's a powerful idea to consider in any software you build. Thanks for joining this explainer.